Hey guys, this is Space Train, your daily express till the edge of the space, and today we will talk about, what is the speed of light? Grab your tickets and let's go. Don't forget to subscribe to get unlimited pass on our expedition. What is speed of light? The speed of light in a vacuum is 186,282 miles per second, 299,792 kilometers per second. Yes, that's a lot. Compared to that, even flesh is running like a turtle, and in theory nothing can travel faster than light. In miles per hour, light speed is, well, a lot. About 670,616,629 miles per hour. If you could travel at the speed of light, you could go around the Earth 7.5 times in 1 second. Early scientists, unable to perceive light's motion, thought it must travel instantaneously. Over time, however, measurements of the motion of these wave-like particles became more and more precise. Thanks to the work of Albert Einstein and others, we now understand light speed to be a theoretical limit. Light speed, a constant called c, is thought to be not achievable by anything with mass. That doesn't stop sci-fi writers, and even some very serious scientists, from imagining alternative theories that would allow for some awfully fast trips around the universe. History of the theory. The first known discourse on the speed of light comes from the ancient Greek philosopher Aristotle, who penned his disagreement with another Greek scientist, Empedocles. Empedocles argued that because light moved, it must take time to travel. Aristotle, believing light to travel instantaneously, disagreed. In 1667, the Italian astronomer Galileo Galilei stood two people on hills less than a mile apart, each holding a shielded lantern. One uncovered his lantern. When the second saw the flash, he uncovered his, as well. By observing how long it took for the light to be seen by the first lantern holder, and factoring out reaction times, he thought he could calculate the speed of light. Unfortunately, Galileo's experimental distance of less than a mile was too small to see a difference, so he could only determine that light traveled at least 10 times faster than sound. In the 1670s, Danish astronomer Ole Romer used eclipses of Jupiter's moon, Io, as a chronometer for the speed of light when he made the first real measurement of the velocity. Over the course of several months, as Io passed behind the giant gas planet, Romer found that the eclipses came later than calculations anticipated, although over the course of several months, they drew closer to the predictions. He determined that light took time to travel from Io to Earth. The eclipses lagged the most when Jupiter and Earth were farthest apart, and were on schedule as they were closer. According to NASA, that gave Romer convincing evidence that light spread in space with a certain velocity. He concluded that light took 10 to 11 minutes to travel from the Sun to Earth, an overestimate since it in fact takes 8 minutes and 19 seconds. But at last scientists had a number to work with. His calculation presented a speed of 125,000 miles per second, 200,000 kilometers per second. In 1728, English physicist James Bradley based his calculations on the change in the apparent position of the stars due Earth's travels around the Sun. He put the speed of light at 185,000 miles per second, 301,000 kilometers per second, accurate to within about 1%. Two attempts in the mid-1800s brought the problem back to Earth. French physicist Hippolyte Fizeau set a beam of light on a rapidly rotating toothed wheel, with a mirror set up 5 miles away to reflect it back to its source. Varying the speed of the wheel allowed Fizeau to calculate how long it took for the light to travel out of the hole, to the adjacent mirror, and back through the gap. Another French physicist, Léon Foucault, used a rotating mirror rather than a wheel. The two independent methods each came within about 1,000 miles per second of the speed of light measured today. Prussian-born Albert Michelson, who grew up in the United States, attempted to replicate Foucault's method in 1879, but used a longer distance, as well as extremely high-quality mirrors and lenses. His result of 186,355 miles per second, 299,910 kilometers per second, was accepted as the most accurate measurement of the speed of light for 40 years, when Michelson remeasured it. An interesting footnote to Michelson's experiment was that he was trying to detect the medium that light traveled through, referred to as luminiferous ether. Instead, his experiment revealed the ether didn't exist. The experiment, and Michelson's body of work, was so revolutionary that he became the only person in history to have won a Nobel Prize for a very precise non-discovery of anything, wrote astrophysicist Ethan Siegel in the Forbes Science blog. Starts with a bang. The experiment itself may have been a complete failure, but what we learned from it was a greater boon to humanity and our understanding of the universe than any success would have been. And so we finally come again to Einstein and special relativity, and I will not bother you to talk about this again. You can check link down below. Although the speed of light is often referred to as the universe's speed limit, the universe actually expands even faster. According to astrophysicist Paul Sutter, the universe expands at roughly 68 kilometers per second per megaparsec, where a megaparsec is 3.26 million light-years. More on that later. So a galaxy 1 megaparsec away appears to be traveling away from the Milky Way at a speed of 68 kilometers per second, while a galaxy 2 megaparsecs away recedes at 136 kilometers per second, and so on. At some point, at some obscene distance, the speed tips over the scales and exceeds the speed of light, all from the natural, regular expansion of space, Sutter wrote. He went on to explain that while special relativity provides an absolute speed limit, general relativity allows for broader distances. A galaxy on the far side of the universe? That's the domain of general relativity, and general relativity says, who cares? That galaxy can have any speed it wants, as long as it stays way far away, and not up next to your face, he wrote. Special relativity doesn't care about the speed of a distant galaxy. And neither should you. We all agree that the speed of light is limit of speed in the universe, but because of time travel is so fascinating, we just don't give up on the idea that one day we will go faster than that. But what happens when you go faster than the speed of light? Because we also have brain limits, we will talk about that in our next video. There are lots of questions left, so don't space out, and leave some space in your brain for answers. I hope you enjoyed this video. If you want to see more, subscribe and click the bell button to get notifications on our latest videos. If you are still here, grab your knowledge and get out of my train.